Okay, so this is lecture 5. So there were a few questions after previous class about transmission lines as to why I took certain liberties in terms of finding out what will be the voltages at different points of the line. So what I am planning to do is maybe spend some part of this lecture to motivate that particular concept, because you'll see it will be it will come back repeatedly as we go through the course, and you will also find some intuition behind the way we are treating it, and it will also help you in your design of subsequent projects, right? So fairly important concept, but fairly simple. So since we are still in the overview mode, I'd like to spend maybe 15-20 minutes on this and then move on. Okay. So the idea of the stuff that we were discussing the other day was, let's say I have VI. There is a source resistance, let me call it RS. There is a transmission line, a long line. I mean, you can assume that's a long line with a return path. You can, if I have to make it more generic, I basically say that if this is and then it ends with RL, right? So this type of modeling is the reason I am putting up this type of modeling is because there is something about transmission line which is not, which is quite, which is quite simple, but it is not evident if you do not represent the transmission line like this. And the part that I'm referring to is this. So if I simply draw the line as a line and I do not show any return path, right? So it might appear to you that whatever is the current flowing in here is the current coming out here, right? But that's actually not the case for all time t, because there are paths from which the current can escape. Okay, so that is something that you should keep in mind. Again, very obvious, but not explicitly written in books. Okay. Fine. So we'll stick to this. We'll stick to this the conventional transmission line picture. The assumption is that there is a return path somewhere in between. So that's why the ideal transmission line picture should be like this. There can be a return path from between, right? So, but we are only treating the transmission line as a delay element, which is okay, given that it behaves like a wire, or behaves like a simple delay element. Let's say it has a characteristic impedance of R0, which is real RS, RL. I will simplify our life. And let's say we apply and a step input ut at time t equal to 0. Okay. What we are interested is to find out what is this voltage V1 and what is this voltage V2 across time. So let's say I wait for infinite time, circuit has settled and all, right? What do you expect the voltage V2 to be, and what do you expect voltage V1 to be? Note that this transmission line is basically an LC, right? It's basically this circuit on top. right? So after infinite time, what do you expect V2 to be? Right, so you expect it to be via UT times, or I shouldn't say UT because we are talking about infinite time. So basically this is RL plus RS plus RL, great. And what do you expect V1 to be? Same, right? You also expect V1 to be also RL. Right? Okay, this is we expect. So now from the transmission line theory, we would like to see whether this expectation is matched or not. Okay? That's the whole agenda of the next 10-15 minutes of today's lecture. Okay, so what I will do is, what I'll do is I'll represent this. There is a standard way of showing how transmission, how the signal propagates. People who work on SerDes and all, they know this, but for the purpose of this class, we'll stick to quite simplistic way of representing the same. So the simplistic way that I am talking about is this. So what I'll do is I will say that let me align this V1 with this node. Let me align V2 with this node. And I would like to plot the time in this direction. Okay. So at time t equal to 0, what do you expect? What do you expect the voltage V1 to be? Note that at time t equal to 0, the waveform that travels in this direction, encounters after RS, it encounters the junction between RS and the transmission line. And the transmission line, by the definition that we saw in the previous lecture, if it doesn't know that the transmission line has an end or not, right? When the signal is at that junction, it is flowing through, it doesn't know what is at the other end of the transmission line. It is still evolving. Circuit is not yet settled. It is still evolving. So which means that for all practical purposes, you can assume that the transmission line may well be infinitely long, right? Because it doesn't know what is at the other end. You can assume that the transmission line is infinitely long. If it is infinitely long transmission line, what is the input impedance of the line? R, right? So at that junction, at time t equal to 0, what should be the voltage then? Right? It should be R0 by RS plus R0. Right? Is that part okay? Okay, so this should be R0 by R0 plus RS. At time t equal to 0, what will be, and let's say there is a delay. The signal takes a delay there is a delay to go from V1 to V2. There is a propagation time. So at time t equal to 0, what should be V2? It should be 0, right? Fine. So after, let's say, time t equal to tau d, what do you expect V2 to be? So one in V2, you would expect this wavefront, right? This wavefront that was at time t equal to 0 here, this guy will move all the way. And after time t equal to tau d, it will reach V2, right? So basically there is a forward going wave, right? So there is a forward going wave. This forward going wave is this guy, right? So that has reached V2 after time t equal to tau d. But at that junction, R0 is not equal to RL. So now it knows that it's not an infinitely long line, right? It sees a discontinuity, right? Before that, it didn't know. Now it knows. Note that this type of this type of argument is different from solving KVL, KCL the way we are used to. Because when we are solving KVL and KCL, like the lumped element that we do not take this into account what happens after the signal has propagated, right? We take the overall picture. assuming the circuit has settled. Here the circuit is still settling. So that's why we can divide this treatment into what is happening after some time and what will happen after some time, and combine all the wave fronts and then figure out what will be the final settled value will be. It is similar to the way we talk about interference and diffraction in schools, right? We say that a wave goes this side, other wave comes this side, and you can basically do the analysis for each of the waves separately and then sum them together, and you see your maxima somewhere, minima somewhere. So similar to that. So you can think of these as wave fronts which are propagating along a line. Yes. Yeah, RS and RL are lumped. What do I mean by lumped? I essentially mean that there's no delay to go from one terminal of the RS to the other terminal of the RS, right? So a negligible delay with respect to the frequency of interest. Good point, right? So that's why we are not bothered about what happens between the wavefront on the left side of the RS and right side of the RS. They're identical. So that's the assumption. So now when I reach V2, there will be some incident wave and some reflected wave. Now, in order to figure out the reflection, I need to know the reflection coefficient. And by definition of reflection coefficient, what is gamma L? That is reflection coefficient at the load side. This is RL minus R0 by RL plus R0. So here, what am I going to see? I'm going to see this guy, R0 by R0 plus RS, right? Plus the reflected wave, so which means essentially 1 plus gamma L. Correct? So let me also make it clear. This part is reflection, and this is incident.
One minus reflection coefficient at the front side times.
We will say that, but when the signal just went through, right, there is no reflection, because in order to have a reflection, you need to have a delay. Right? If there is no delay, the concept of signal traveling and returning back doesn't exist. If you want to impose reflection there, right, I presume the question that you are thinking is, why didn't I put the reflection coefficient concept for the forward going wave at V1? If you want to put that, what you can assume is that there is a small stretch of transmission line after RS, which is matched to RS, right? And then you are going to have a reflection between that transmission line and the actual transmission line, and you can then go about doing it. Right? So that's why that lumped element approximation is important, right? If the transmission line goes to almost zero, there is no forward going and reflecting, and a reverse going wave. So whatever happens instantaneously. Okay. But good question. Fine. So now there is a reflected wave at V2. The reflected wave is traveling to the left, right? So when the reflected wave travels to the left, what am I going to see after 2 tau d at V1? So what's going to happen after 2 tau d? The reflected wave is going to reach V1, but V1 already had something, but this is the unit step that I had applied, right? So the unit step doesn't vanish off. So this part still remains. I add the reflected wave, right? I add whatever came here to it, and then basically there will be another set of reflection. I add the original plus the incident plus reflected at that node, right? So I basically say that at 2 tau d, I will have this R0 plus RS. This is the original. So this is this guy. Plus the reflected part. Reflected part was R0 by R0 plus RS, gamma L. That was coming from the load end. But again, this, whatever was traveling this side, will again get reflected, right? Part of it is again going to get reflected. What is that part that is going to get reflected? The reflection coefficient at that node times whatever was incident, right? So basically at that node, the reflection coefficient is gamma S. times whatever was coming in. So which is, which is effectively that plus 1. So I should say, yeah, 1 plus gamma s, right? So what is gamma s? I should define gamma s. Gamma s is Rs minus R naught by Rs plus R. Okay. So among these, whatever has accumulated at V1, some part is going to move to the right. What is going to move to the right? The one that got reflected at that junction, right? So the one that got reflected at that junction is going to move to the right. So what is that part? I am only writing the reflected part, otherwise it's getting bigger and bigger. So I'll just say something plus the reflected part is this guy, right? So it will be R naught by R naught plus Rs times gamma S. But again, it goes to the load end. This is the incident wave at the load end now, plus the reflected part. So this is 1 plus, sorry, so this is, there is a gamma L associated with it, right? Gamma L, gamma S, which is the one that is going to the right, and then 1 plus gamma L. Right? Make sense? So essentially, this keeps on happening for infinite time. Right? So after these infinite reflections, I'm going to get a settled value. So what will be, this is after infinite reflections, what will be V2? V2 will be basically summation of everything, that summation of all reflections. I mean, whatever came and whatever reflected back, and I add them up, right? So what should that be? That should essentially be this R naught by R naught plus Rs. So this guy, 1 plus gamma L, plus this is the second reflection. So R naught by R naught plus Rs gamma L gamma S times 1 plus gamma L. Plus, if you go on, you are going to see, you're going to I'll just write the next term. It should be intuitive now, but you can verify it doing it yourself once again. This will be gamma L gamma S whole squared, because another set of reflections. And this 1 plus gamma L will again appear because this is summation of, this is the incident, this is the reflection. So this is going to always appear at that load end. And gamma S whole squared is basically the effect of the amount of signal that is lost while at every reflection, right? Or rather, the amount of reflection that returns after every reflection. Okay, so essentially now you see that this is an infinite series. So I basically can write it as R naught by R naught plus Rs 1 plus gamma L times 1 plus gamma L gamma S. Right? This I can write because gamma L, gamma S is, both of them are individually less than 1. So it's a convergent series. So I can basically write this is equal to 1 minus gamma L, gamma S. Now I can, if I replace these values, right, you can do the algebra yourself. If I replace these values, this will come out to be, let me just do it for you, maybe that would have some continuity. So 1 plus gamma L is essentially RL minus R naught by RL plus R naught minus this becomes twice RL by RL plus R naught. And this becomes on the numerator RL plus R naught, RS plus R naught. So this cancels, this cancels, this cancels. This also cancels. So we get twice R naught RL by twice RL R naught plus twice R naught RS. So I can basically cancel 2 and R naught from numerator and denominator, and this comes out to be RL by R naught plus RS. Right? So you see, after this very simple thing that we normally do with resistor divider, you can come up to the same conclusion at steady state when you do use transmission lines also. And this is a much more generic way of dealing with circuits, because truly in each circuit, you are going to have delays. There is no getting away from it. Just the lumped element approximation helps us to say that the delay is 0, right? So if the delay is 0, what intuitively, visually, what's going to happen? So visually, if you think about it, if I think about it, so at V2, right? So let me redraw it here. So at V2, what are we going to see? We are going to see at 0, we are going to see 0. After tau d, I am going to see a step. And what will be the height of that step after tau d? What will be the height of that step? It will be R naught by R naught plus RS times 1 plus gamma L, right? So this will be R naught by R naught plus RS, 1 plus gamma L. After additional 2 tau d, right? This reflected wave goes back and comes back. That takes another 2 tau d. So this is basically 3 tau d. So this will hold here. There will be another small bump, right? And then after again another 2 tau d, there will be another small bump. And each of these bumps are going to get progressively smaller. And eventually it is going to settle to, after time t equal to infinity, it is going to settle to R2 by, or rather RL by RL plus RS, right? Okay. So if this tau d's were negligibly small, these progressive bumps wouldn't have been distinguishable, and you would have got a step right at the moment of application of the input, right? So in a lumped element approximation, we neglect these steps, right? And the moment we apply the input, we get the output. Yes. Ah, right. Yeah. Thank you. Yeah. Yeah, I got ahead of myself. Fine. So now the question that another question that came in the end of the last class was what about those tan hyperbolics that we learn in books, textbooks, which are also valid, but those equations are valid for sinusoidal waveforms, right? So let's assume that we have a sinusoidal waveform instead of a step, right? In the previous class, we did a delta where we could clearly see echoes. The effect of echoes are not particularly visible in a step. It seems like the step is trying to come up to whatever it was initially trying to get to, right? So this effect of delay um, emerges as different types of phenomena depending upon the type of inputs that you apply, right? If you apply a small one pulse kind of input, you are going to see echoes of that. If you are going to apply a step side of input, you are going to see settling. If you are going to apply a sinusoidal waveform, right, what's going to happen? So if you apply a sinusoidal waveform has an infinite, it basically you have to do an infinite, you have to take the waveform which is infinitely long, right? So if it's an infinitely long waveform, so for every, so basically there is no time t equal to 0 per se, right? So it goes on from t equal to minus infinity to plus infinity for a steady state response. But for each, if you could think that you are riding this waveform, right? You are riding this crest. You are not anywhere else, but you are riding that crest, then you can follow that crest. And that crest will seem like so this crest will appear here at time t equal to tau 1, at time t equal to 0, but that crest will appear maybe after some time after tau d, right? And then this guy is going to reflect, and then this is going to happen, keep on going, right? So ultimately, eventually you are going to get all the summation of all the terms, right? Each of those terms are a sinusoid. So you can assume that you are summing up infinite sinusoids. So what can happen potentially if you sum up infinite sinusoids? You can get constructive or destructive interference depending upon this delay, right? So depending upon this delay and the frequency of interest. For example, a trivial case is this. Let's say I am just taking a match load here, a match transmission line. This, let's say this is R and this is also R. And this is open circuit here, right? Let's say this is open circuit here. And you apply a sinusoid. And again, let's say I am riding this crest. Okay. So at time t equal to 0, this waveform essentially will be what now? If this is 2 Vp, what will be the time t equal to 0 waveform? It will be Vp, right? It will be divided by 2 at time t equal to 0, right? Forward going wave, right? So essentially it will be exactly aligned with the input, but this will be Vp. After tau d, this guy is going to appear here, but there will be again a reflection, and the reflection will be exactly similar to that of it's identical to the forward going wave because this gamma L is infinite, right? So you are going to get a waveform which is delayed in time. But what will be so now the crest is here, it has moved in time. What will be the amplitude here? think about it carefully. The forward going wave has an amplitude of Vp. The reflected wave also has an amplitude of Vp, and they are adding up. You should have, they're adding up in phase, right? It's not opposite phase. Reflection coefficient is +1. You are going to get 2 Vp here. But the reflected wave will have amplitude of Vp. It will have peak to peak of Vp, because this 2 Vp is both addition of reflection and incident. So this guy, whatever comes back, will come back after some delay. By the time it reaches here, maybe the crest has reached here. Okay. So now assume that the delay is such that it is exactly equal to half time period of the waveform, of the frequency. Right? If the delay is exactly equal to half time period, what are you going to get at the output at V1? So basically what I'm saying is that this is one waveform, and I delay this waveform by half time period. What am I going to see? Right? So this is half time period delay. Tau d is equal to, so tau d, if this delay of going forward going wave and the reflected wave is half time period, what is tau d? What is the delay in terms of tau d? No. What I'm saying is that what is the delay between the forward going wave and the reflected wave in terms of tau d? 2 tau d, right? It goes and reflects back, 2 tau d. So 2 tau d is equal to half time period. So 2 tau d is equal to half time period, which means tau d equal to quarter time period, right? It's a quarter time period. In terms of, since it's an electromagnetic wave, I can associate wavelength with the time. So this is equivalent to, in terms of wavelength, quarter wave transmission line, right? So essentially, a quarter wave transmission line, which is open circuited at one end, gives you destructive interference at the input side, right? So essentially, the combined waveform, now we are not talking about the incident and the reflected. I'm talking about combined waveform. So what am I seeing? I'm seeing a so now let's say combined picture. So let's say I don't know, there is a box. I don't know what is inside the box. Okay. I have some current is going in. I don't know what current. I mean, maybe some current is going in, I in, but I observe the voltage here, V1. What is V1? What is V1? 0, right? Destructively interfere. So this is 0. So finite current is going in, total finite current, but voltage is 0, which means what does it look like? Short circuit, right? It behaves like a short circuit. So this behaves like a this. Okay. Similarly, you can do the exercise yourself. What happens if we have a short circuit at the load side, right? You are going to see that it will behave like an open circuit at the source side, right? So, and similarly, you can also do, if you have a generic impedance, let's say you take a λ/4 line, and put some generic load at the load side, ZL. You are going to see that if you do the same exercise after infinite reflections, the effective impedance that you are going to get will be Z0 squared over ZL. So that is one of the standard formulas that we use. So that's why λ/4 line is often referred to as an impedance transformer, right? Whatever is short circuit behaves like an open circuit, right? Short circuit at one end behaves like an open circuit at the other end. Open circuit at this end behaves like a short circuit at the other end. Similarly, if you put you'll see that if you put an inductor at this end, it will behave like a capacitor at the other end. If you put a capacitor at this end, it will behave like an inductor at the other end. So that is one of the reasons why this is one of the most popular architectures if you want to do some sort of impedance transformation. Okay, you are going to see later on where these are used, but I am not proving those, right? Those are textbook stuff. You can also do it yourself without going into the hyperbolic formulas. You can do it by this multiple reflection thing, and that's a very good exercise. It gives you a lot of intuition, and you can do these simulations also in Cadence or any other simulation software. You apply a pulse and see the reflections, right? It's very interesting to see actually that these transmission lines are not really theoretical concepts. They actually have, you can actually see wavefronts moving. Okay, any other questions? Okay, fine. So if there are no questions, let's move on. So before, again, I mean, to tie things together, I have only taken voltages into account till now, right? If I have to take currents into account also, everything remains the same, just that in case of a current, just like you have VI, this is V1 plus, this is V1 minus. So your total voltage here is so let's call it V1 total. V1 plus V1 minus. In case of a current, this current is V1 plus over Z0, assuming this is Z0. And this current is minus of V1 plus over Z0. So your current total is V1 plus over Z0 minus V1 minus over Z0. So this is the only difference between current wavefronts and voltage wavefronts. Analysis remains the same. Do the same thing, you are going to get same answers. Okay. Yes. I haven't said we would like to avoid or not. It depends on your application. Sometimes you like to avoid, sometimes you won't like to avoid, but go ahead. Yeah, true. I mean, but we are not talking about amplifiers here. What I'm saying is that what can happen if you have a transmission line. So, and while doing this analysis, we came up with an application. That's all. Or rather, haven't really come up with an application, but have figured out a way of making something look like something. And that might have an application. Okay. So another, I mean, an application that you can directly think of, let's say you have a blocker at a frequency, and you design your transmission line in such a way that for that particular frequency of the blocker, it looks like a short circuit at the input. So the blocker will get notched out, right? And if you then, if you can tap it from here, if you tap your signal from here, and the signal is at a different frequency, the signal will not get notched out because for signal, the wavelength is different, but the blocker gets notched out. Right? It's one direct application of how you can use it in RF to filter out blockers of a known frequency. Okay, so this type of applications are regularly used in when you have power amplifiers plus an LNA on a single chip. Typically, you will see in most cases power amplifiers are kept at a different chip. But if you have a power amplifier and a LNA on a single chip, and you know that power amplifier output, your power amplifier signal, which is at a much higher voltage level or a power level, is at a different frequency than LNA, sufficiently different frequency than LNA, then you can put this lambda by 4 transmission line open circuit and notch it out. And that is also done. But one caveat is that, I mean, I have assumed they are lossless and all, but in principle, all of them are lossy. So this perfect cancellation is never going to happen. But something is better than nothing. You are going to get something. Okay. But I find this delay picture of transmission line very intuitive. And even though the math sometimes will lead you to, not sometimes, always will lead you to infinite series, but it gives you a real life feel of how circuits actually work. Okay. Okay, fine. Any other questions? We actually will use it for high frequency only.
Very less, right?
Yes.
How you can make that much small?
Okay. So it depends upon now. I haven't talked about what is the length, actual length, right? So we can see, right? So let's say if you are talking about 30 gigahertz, and if we assume that, I mean, all the mu n and permeability are same as free space, which is not same, but let's assume that. So 30 gigahertz translates to 1 millimeter, right? So 1 millimeter is lambda. So lambda by 4 is like 250 micron. So now we are talking about inside the chip dimensions, right? So you can use 250 micron line to notch out a blocker at, let's say, 30 gig, right? And just an example, but typically lambda by 4 lines are, I would argue there's the other way, the problem is at the other end, what you are saying. We cannot use it at a lower frequency because lambda becomes very high. You cannot use this on a chip for a 1 gigahertz solution. So then the lambda becomes few centimeters and your chip sizes are maybe 2 millimeters square. Right? So that's why in most RF applications, you see tuners, they are pretty big. The reason it is big is if you are trying to deal with circuits which are of a few gigahertz, sub 10 gigahertz, naturally they have to be big in size. So very often tuners are off chip so that you want to do some impedance transformation the way you want. Okay. So the problem is at the other end. If you want to go to 30 gig, 60 gig, 100 gig, very convenient to use lambda by 4 transmission lines because they are very manageable dimensions. But if you go to even higher, let's say terahertz, then it becomes a problem because everything becomes a transmission line then, right? So maybe you don't want transmission line effect, but it will become transmission line. Okay, fine. So let's start putting the picture together.
So
yes.
Two transmission lines. Like suppose we replace that lambda with a transmission line. And two transmission lines have different characteristic impedance. Suppose R1 and R2.
You mean this? You have one transmission line here, another transmission line here, is it? Okay.
You can replace that R with the transmission line.
Let's say another transmission line.
Like in the single teacher.
Right. So when if you are talking about forward going wave, looking in impedance is still Z0 because it doesn't know what is the other end. Right? Total impedance will be different. Right? Because whatever is coming back will depend upon what is getting reflected here, what is getting reflected here. And that will be a function of the Z1 or maybe after whatever is connected there. So the combined impedance by very definition, the impedance that we know of is what happens to a settled circuit. Right? So after everything has settled infinite time, the ratio of voltage and current is the way we define impedance at steady state impedance. Right? The steady state impedance will be a function of Z0, Z1, whatever is connected. But if I say that I am only looking at instantaneous impedance, if you can think of it that way, what is the impedance that the forward going wavefront is seeing? It is still going to see Z0 because it doesn't know what it is at the other end.
So we have a wave at the middle point of the transmission line.
Yes.
The wave going forward will see impedance of Z1.
Yeah.
Going the other way around will see a Z0.
Sure. So you'll have a reflection coefficient there, right? So reflection coefficient will be between Z1 and Z0 then.
It doesn't care like what is lying at the other
At that junction, it doesn't care. Right. So the way to think about it is, I mean, this is exactly the same as, let's say you have a wall and you have a rope connected to it, and you give a jerk to the rope. Right. So this jerk is going to travel in time, right? Until the time it reaches the wall, it doesn't know what's connected there. Right. If it's a perfect wall, so the reflection will be like this, and these two will add up, and there will be no jerks at the wall end. but you are going to see this waveform will come back after some time at the source site, right? But if this wall if the wall is not a perfect wall, maybe it's another rope of a heavier density, and then it is connected to a wall. So the some part of the reflection will come back and some will go forward, right? And then, but whatever is going forward or whatever is coming back doesn't know what's connected to the other end of the second rope, right? So that's the difference. Okay. Fine. So the reason this is important is because of this. So you have an antenna. You're coming back to the receiver picture. You have a chip. The antenna typically sits off chip. If you are talking about few gigahertz, sub 10 gigahertz frequency ranges, antennas are still of the order of centimeters, cannot be integrated in a chip. So antenna sits off chip. You have a SAW filter that we discussed in the last class, centered around FC, and you have a long transmission line, right? And then we would like to have an amplifier, and we call this LNA, right? And we said that in order to minimize reflection at the LNA side, we have to ensure that this impedance is exactly equal to Z0. Otherwise, you are going to have this, and you are going to have these multiple pulses, multiple echoes at the LNA input, which may or may not be good, right? So it can amplify your signal, or it can destructively, it can reduce some part of your signal, depending upon how many reflections you have. Okay. So since you cannot control what the vendor is putting at the other end of the transmission line, you have to ensure that you do your job and make it matched, so that there is no further reflection at the LNA transmission line interface. Okay, fine. So now the question, so basically then it boils down to what should be the characteristics of the LNA, right? So LNA is basically, firstly, it's a low noise. It has to be low noise because it is dealing with signals of extremely small amplitudes, right? Voltage amplitudes are power numbers are of the order of -90 dBm or so. So the voltage amplitudes are really low, right? So extremely low noise. And then it needs to have matched input impedance. Which means that a simple common source amplifier is not going to do, right? So a common source amplifier has a input impedance of ideally infinite, and if you go to gigahertz levels of frequency, nothing is either zero or nothing is infinite. You are going to have a capacitor, right? So you are going to have an imaginary impedance, right? Some j omega something, 1 over j omega something, you're going to get it. So the moot point is that it's not matched. So which essentially means that you have to put some circuit in between the transmission line and your common source amplifier, or maybe change the architecture of the common source amplifier to ensure matching is there. So what I'm going to do is I'm going to say that, so here you need a matching network. Then you go to LNA. Now this matching network needs to be on chip, ideally. If you are planning to place it off chip, you have to ensure that it is extremely close to the chip, so that you don't see reflection between the line of matching network and the LNA, right? If the line between matching network and the LNA is also of the order of λ/4 or something like that, right? Then you can have trouble, right? So you have to, if it's on the chip, typically not a problem because these dimensions are of the order of millimeter or hundreds of micrometer, right? It's less than millimeter. typically this L is typically has to be much lesser than 1 millimeter. Typically, they are much lesser than 1 millimeter. The size of the chip itself is of the order of millimeter or few millimeter. You cannot really take the entire chip out. So by default, it becomes much less than a millimeter. So you do not have a problem. So why is this important? This is important because you have to worry about matching at this junction. But do you have to worry about matching at this junction? You don't need to, because there is no delay. When I say I'm working at a much lower frequency, what I'm saying is the waveform is so long that the forward going and the reflected going wave fronts, they look identical. There is no delay between the crest and the trough and so on, right? So there is no echo. There is obviously an echo, but the echo is not, the echo overlaps exactly on top of the incident wave. Okay, so you don't see any difference. There is no possibility of any destructive interference. Right? So, or any other kind of other kind of signal interference with respect to the forward going and the reflected wave, other than constructive interference. Only constructive interference can happen if you have no delay between the forward and the echo, which essentially means that there is no echo. You can treat it as a lumped circuit, by R1 by R1 plus R2 directly, similar to that. So no, yes. So what is high frequency? That means, right? So that's why that was his question, right? So what is meant by high frequency in this case? This will become a problem if lambda becomes of the order of a millimeter or so, right? Lambda of the order of a millimeter means 30 gigahertz, even higher. So if you are, they are typically called millimeter wave circuits. That's why. So because the lambda becomes of the order of a millimeter, the popular lingo is, we call it a millimeter wave circuit. In millimeter wave circuit, you have to be conscious about what is the length of the transmission line, else you are going to have problems. But if you are talking about, let's say, sub 10 gigahertz, not an issue. You can basically go ahead with the lumped element approximation. Another thing is, you are going to have, chip doesn't necessarily always contain matching network and LNA. You have all sorts of other stuff. We'll see what are the other stuff. But whatever is loading the LNA is also sitting on the chip. Do I need to bother about matching at this junction? I don't. But let's say you are somebody who is selling an LNA for a living, right? Which means that you have an LNA, which you go to one of those websites where you can get Mozart, DZKey, or mini circuits, wherever you can buy separate blocks for your experiments. Which means that the LNA is an isolated circuit. It is connected by a transmission line in the PCB at the input. It is connected to the transmission line at the output also. Then what do you need to ensure? The output of the LNA also matches to the transmission line. If it's an off-chip LNA, right, you have to ensure both the input impedance and the output impedance are matched, because they are driving external environment which is not in your control, right? But if it is inside the chip, you need not bother, as long as the transmission line effects can be neglected. Okay, another important design takeaway, right? So because this can have your design implications, you do not need, if you know that whatever the LNA is driving is in the chip, you do not have to bother about putting in extra brain power to match, right? If it is off chip, then you need to. Okay. Okay, fine. So we'll study LNA in future lectures, but now what should succeed the LNA? So we have an LNA. So what is the input here? Input. Now note that we were transmitting signals at FC plus minus Fin, where FC was a carrier frequency and Fin was a baseband or a signal frequency, which is at a much lower frequency than FC, right? So FBB much lesser than FC. Okay. So now the information is FBB. So this is the signal frequency which has information. Okay. So if that is the case, what should follow the LNA? FC, why did we have FC? to translate to just because antennas are becoming big. If the antennas are small, we didn't have bothered, right? To some extent. I mean, if I have to stay clear of the legalities, yeah, to some extent, because I do not want to impinge on somebody else's frequency spectrum. But from an engineering aspect, your FC, we needed an FC simply because the antennas were becoming big. There is no other reason, right? Because everything is difficult at high frequencies. Why do I need to go to high frequencies? But the only thing that is easier is size of the antenna is smaller, right? So you transmit. Once you receive and you are inside the chip, you need not do anything at FC anymore, right? You are not transmitting inside the chip, right? You would like to ensure nothing is transmitted inside the chip, right? Because it can lead to interference and other issues. So, which means that you have to come back from FC plus minus FBB to FBB, right? So what do you need to do then? You need some sort of frequency translation again. You need to down convert, right? So you need to have a mixer again, just like you had a mixer at the transmitter side, you need to have a mixer at the receiver side. Okay. So yes. 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 We'll see. That's my next question. So let's say you have a mixer, and your mixer is typically what? Typically a square wave, right? We saw it in the transmitter's end, right? So ST. And what should be the period of the square wave? Ideally, one over FC, right? So TC, which is 1 over FC, right? It's 1 over FC. So that is fundamental frequency is FC, right? So essentially, I can say I have frequency components at FC. Maybe I have 3 FC. If it is square wave, let me just say 2 FC also. I mean, need not necessarily be ideal square wave. Ideal 50% duty cycle and so on. Okay. So which means that at the output of the mixer, what are you going to see? So let me draw the two frequency components. This is FC plus FBB, right? So this is FC. So this was the input. Around FC, I'm only drawing the positive side. And your square wave has frequency components at FC, at twice FC, at thrice FC, and so on. So what are you going to see you are going to have here also, right? You're going to have something here. So what are you going to see at the output of the mixer? Which frequency components? Right. So you are going to see NFC plus minus FBB. And so essentially what is going to happen is, if only these were present, let's say, forget about the other tones, if only these were present, it would have mixed and come back around DC, right? So one part would have come around here, and another part would have gone to 2FC, right? So you would have gone to 2FC. That's why something would have gone here. If only that were present, but there are other frequency components also, they will also come back, go at different frequencies. If I concentrate only on these two, right? So similarly, you're going to have here negative frequency also, you're going to see. This is FBB, this is minus FBB. So now let me come back to Dhruv's question. So obviously you are going to have higher frequency components. Which one is of our interest? Only the low frequency one. So what should I do? I should have a low pass filter. Do I need a SAW filter here? We don't need, because these are very, FBB, let's say, is a megahertz, FC is probably a gigahertz, right? So they are not separated with a very small frequency interval with respect to the center frequency, right? So one frequency is, the one that I want to filter out is at 100 times higher frequency than whatever I want to let pass through, right? So I don't need a very sharp filter. More or less shallow filter is going to do, which means I need to put a filter here. So which naturally means that the architecture evolves to You have a SAW filter, your transmission line, you are inside that, you have a matching network, you have an LNA, then you have a low pass filter. Sorry, I have a mixer. Then you have a low pass filter, right? So at low pass filter, what are you going to get? You are going to get an analog waveform, right? You are going to get an analog waveform that you had transmitted at the transmitter end. Okay. So here essentially your receiving is complete, but we all know that we don't store our information in analog form in our cell phones, right? We store it in digital form. We have memory cards that can only read ones and zeros, right? Or high voltage, low voltage. Right? So essentially, after this, you need an ADC. For ADC, you will need a sampler, and you basically then say that and if let's say the sampler is a part of the ADC, this is not an ADC course, so we'll just leave it to Ashwin. You have n bits. If it's an n-bit ADC, I mean, I think we all know that the very famous formula of SNR equal to 6n plus 1.7 something. So now depending upon how much accuracy you want in the ADC, I mean, how much accuracy you want in your signal that you are receiving, you build an ADC for that number of bits, right? So once you have an output of the ADC, what do? You put, these are all ones and zeros bits. So they go and store in the memory. Okay. Yes. Here? Yes, we assume there is only signal. Why can we assume that? Yes, we have already used one SAW filter upfront. But that's a good question. The reason it is good is because, as it turns out, the SAW filter cannot filter out everything very well. So the filtering is actually distributed. Now that becomes a system choice. You want to place it slightly before LNA, slightly after LNA, so on, right? So that is something that often, if you look at the actually implemented architectures of receivers, you will see filters spread around the signal chain. Okay, but I mean, this is a very top level overview of assuming that the blockers have been filtered out at the input of the LNA, right? Okay, fine. So now this becomes, you have things in the memory. So now what is the overall architecture then of the entire transceiver, that is transmitter plus receiver? So you have this thing. You have a SAW filter. I'm not showing the transmission line anymore. Assume that it is there. Then you have a matching network. Then you have an LNA. Then you have a mixer. Then you have an LPF. Then you have an ADC. And then you have a memory. And quite often, when you are transmitting, you are not necessarily transmitting what you are live recording. You are transmitting things which have been stored. That is, you are also interfacing with the memory. You are pulling from the memory and you are transmitting. So that's why, even though you have a sensor, you can modify this same thing as saying that you are basically taking the output of the memory. And these are all digital bits. And using a digital to analog converter, that is a DAC, you get it to analog waveform, right? So typically, the DAC waveforms are not sinusoidal. They are also square wave-ish. So you need another LPF here. Output of the low-pass filter is your baseband actual waveform. That is sinusoid, right? So this is at FBB. So you essentially then put a mixer, right? At the and then after at the So the things that come out of the mixer again have multiple components. So you again put a low pass filter, then you put a PA. Right? So once it comes out of the PA, depending upon what type of PA you want, right? If it's a switching PA, you need another set of filters, or this filter need not be there. A filter can be placed outside the after the PA. As it turns out, you would also need another SAW filter, because you need a sharp filter at the output of the PA, because you are transmitting really high power with respect to whatever you are receiving, which means that even a 50 dB suppression of the PA power might not be enough, because you are essentially receiving 90 dBm, minus 90 dBm, minus 100 dBm kind of signals. So you typically put another SAW filter here, and then you apply to the antenna. Okay. Again, you are going to see that antenna in a chip, in a system, antenna takes the most amount of area, antenna the transmission line. So ideally, you would like to use one antenna, not two, if possible. So essentially, you would like to use the same antenna for transmitting and receiving. And these SAW filters are at slightly different frequencies. So this is FC plus, let's say, F receive. This is FC plus F transmit. And you do not transmit or receive at the same frequency. That is why you don't transmit and receive at the same frequency. And that is why these local oscillator signals are F receive and FTX are of slightly different frequencies. Yes.
Show the architecture at the upcoming version, it is FC time now.
Yeah.
So here the down conversion, it is from textbook to it is minus FC.
Yeah. So whenever you see minus FC, you are basically, if you instead of putting sinusoidals, if you use complex exponential, right, e power FC plus something, then in order to get that e power FC to DC, you have to multiply with minus FC, right? In principle, that is what it is happening, right? But if you are talking about real signals, then nothing is negative frequency. Everything is positive frequency. It is assumed that it has both positive and negative components when you write trigonometry, right? So but another system level thing that came out right now is because you are not transmitting. I should write TX here and RX here. I made a mistake here. Hold on. Yeah. So this should be FTX. This is RX plus. This is FTX plus R2. Yes.
Don't we need a matching network after PA?
Good question. His question is, don't we need a matching network after PA? So it is not very evident why we don't need it now, right now, but when we deal with PA, we are going to see. But let me ask you, why would you want a matching network after PA? Yes. Yes, right. So his question is, what about the matching network here? If you do not have a matching network here, the signal can go in and come out, which can happen. But as it turns out, this should be intuitive that when you match using simply R and R line, right, you are all basically losing half the signal in terms of amplitude, right? So you are, in terms of power, you are losing 1/4. So that's a trade-off if you are planning to do matching using in the PA system, because PA is already so poor in efficiency. Just for matching, you are even losing 50% of what you could have sent, right? So that is a trade-off that designers have to deal with. So you have to be ensure that even without using matching, the PA operates properly. So that's why there is a term that is used for designing PA. It is called load pull. Just think of it as ensuring that you are tuning the output impedance of the PA to operate at a maximum frequency without ensuring there is no untoward effects of reflection. There will be reflection, it is understood, but you have to place your whatever things that you are placing outside the PA in such a position that they do not cause adverse effects to the PA. That's the trade-off. But you are correct. So ideally, we should have put a matching network, but matching network has that trade-off of you lose power.
Could as well modify the output impedance of the PA.
To some extent we do, but it's not in our control what is after the PA. There will be a transmission line, but we know that to some extent that is 50 ohm, right? But I don't know what is at the other end of the transmission line. So typically that's why PA design becomes much more critical, right? So the good thing about PA is that you do not have to bother about blockers because PA itself is such a high power device. So you say that, okay, there will be reflection that comes back to the PA as long as whatever is reflected and coming back to the output of the PA is not large enough, we are good. Right? So that's the trade-off, right? But that's a problem in high power PA designs, right? Because what can happen if you are, let's say, designing a very high power PA. When I say very high power, I don't mean like power, I don't mean like megawatts. Let's say even a watt of PA power. Then if the reflection is another 1 watt or of the order of a watt, then the amplitude at the output of the PA can be so high that it can break down the PA. So then you have to ensure that safeguards are put in place so that that doesn't happen. Then you say that, okay, whatever is the SAW filter that you are putting after the PA should be able to absorb to some extent some reflection. Or you put some small matching net, not a matching network, but a reflection absorber at the output of the PA. Right. So those type of things come up while designing PA. The only reason they come up is that we need to ensure PAs operate at very high efficiency, and efficiency and matching are sometimes they trade each other off. Okay.
So the reflection is in such a way that the output voltage is increasing.
Yes.
You can as well reduce the gain of the PA.
That we don't want to do. Well, again, it's a design trade-off, right? If you want to reduce the gain of the PA, then you are effectively saying whatever is driving the PA needs to drive a needs to have a high swing. Right? Because let's say at the output of the PA, I want a swing of plus minus 1 volt. And I say that the gain of the PA is 10, right? Not dB, 10. So which means you are anticipating the input to be plus minus 100 millivolt. Now, if you say that I'm reducing the gain of the PA, which means I'm to 5, then I am expecting the input to be plus minus 200 millivolt, because the output power output of the PA I don't want to compromise because that's a spec.
But we are utilizing the reflected wave to gain output power.
But you are utilizing the reflected wave to gain output power, but that output power is not going to the antenna. Right? That is coming back to the PA, right? You would want the output power to go to the antenna. Right? It's no good having very high output at the PA, but nothing goes to the antenna. Right? So that's a problem. Okay, fine. So quite often, again, you are going to see that in architectures, if you look at data sheets of transceivers, you will see that these two are also combined into one single filter, and that's called a duplexer. Two SAW filters combined together. It's called a duplexer. And I shouldn't say two SAW filters combined together is called a duplexer. A duplexer is something that allows signals to flow in one direction and not the other in some way. So that is ensured to some extent by, so the sign is something similar to this. So you assume that this is RX, this is TX band, and it's a 3-port device. Your antenna is connected here. And you have maybe RX, and you have TX. And you have your microprocessor or whatever digital circuit sitting here, which is doing all the hard DSP stuff. Okay, fine. So that kind of ends the overview of a transceiver, right, or the RF chain. Only part that I didn't touch upon at all is how to design. I mean, what are the design constraints of generating these FLOs or FRX or FCs, right? So we just assume that the sinusoid exists, the carrier frequency exists, which is not we have to design that also. So what I'll do in the next class on Thursday, I will just spend another 15-20 minutes on giving you an intuition behind what is the how do you generate those and what are the consequences of those, and how the generation, the constraints of the generation of those multipliers affect the overall architecture. That is also a thing. There are architecture choices to be made based on the imperfections of of the generation of the carrier frequency. There are a couple architectures we are going to talk upon and then move on to LM. Yes, question.
One is that receive and one is that transmit.
Yeah.
So how does communication take place? I mean, we are transmitting at a different frequency, but receiving has to be done at different frequency.
Yeah.
So don't that create a problem?
No, it doesn't create a problem generally because when you are transmitting, you don't, let me rephrase his question. His question is very, I mean, it should be apparent to everybody that this can be a problem the way I have talked about it. His question is, let's say you think about yourself and your friend sitting in two different rooms. You are transmitting at a different frequency, but your friend can only hear at a different frequency, right? So will the communication take place? It will not take place, right? So that's why you don't have the channel directly between transmitter and receiver. There is a base station. So that change happens at the base station, right? So you have a tower, and then is a base station. At the back end, they change it, and then they transmit at the frequency of reception. But good question. Yeah, thank you. Question? Yes. No. Okay, fine. But I think you are making a statement that we have time. Okay. Okay.